right, good afternoon everybody. Welcome back to another edition of our live science demos. If you take a look around, it might look a little different today though. We're coming at you live from our lab at home, aka my kitchen, where all you cool scientists at home can be doing your own experiments. Make sure you're looking out for our virtual science demos that you can follow along with at home. We posted an awesome one yesterday. You're also probably wondering, where is Hydrogen Harry? Well, I can assure you he is safe at home. We are practicing social distancing here for the good of ourselves and everyone around us. So I'm going to be flying solo today, but you can check him out next week if you look for him on our live science demo. So welcome. Today we are going to be doing some chemistry. So we're going to be talking about chemical and physical changes. So before we begin, as always, safety first. So I'll get my gloves on here because we are going to be working with some interesting chemicals here. Some strange stuff, if you will. But it is really awesome. And hopefully we get some cool visuals for you. Safety goggles, engaged. Awesome. All right, so we're going to be talking about physical versus chemical changes. So comment down below before I explain anything if you know the difference between a physical or a chemical change. And if you can give me an example of one of each, that would be awesome. So our physical changes are going to be changes that we can revert back to their original state. So what does that mean, to revert back to something? Well, it means we can change it back. And usually it takes the same amount of energy or even less energy to get it back to its original state. So what would be an example of a physical change? Let's find out. So I've got some beakers and flasks set up here. So for our first experiment, this is something super simple that you can definitely try at home. Now I'm not going to say that about everything, but this one, I encourage you, try it at home. So what I have in my flask here is actually water. So it's warm water in there. And then inside of my balloon, I've got salt. So again, comment down below, what do you think is going to happen when I pour that salt into the water? Will we get a big explosion? Are we going to get a color change? Do we have bubbles form? Let's find out. So we can have that salt pour into there. And if I stir it well enough, we can see not much happened. Our balloon still looks the same. Still water in there. We used Himalayan pink salt, so the water's a little bit pink. But nothing really happened. So how can we get that salt back out of that water? How can we get the salt back out of that water? And is it even possible? Absolutely. What we could do, we could take it on our stove. I'd have to clean up my little mess here. But we could place this on our stove, heat that water up, and the water is going to evaporate. But the salt will stay behind. So we can get our water back, and we can get our salt back. We can get our two original ingredients, which means it is a physical change. Yes. What we're going to try with this one, we're going to see if we can make a chemical change happen. Now there's a couple things to look for when we're creating a chemical change. The first thing is creation of a new state of matter. So what I have here is some baking soda in my balloon, and then I've got vinegar in here, so baking soda and vinegar. And again, this is one that you can try at home, and in fact, I encourage you to try it at home. So we're going to do just like we did with our salt and water, and we're going to see if anything happens. So again, what we're looking for in a chemical change, are we going to create a new state of matter? So we're mixing a solid with a liquid. What's our third state of matter that we're missing there that might be able to be produced in here? Remember, we talked about those states of matter, and we even learned a fourth state of matter last week. So if I mix these together, we want to see, is there a new form of matter that's created? Is there a temperature change, number 2? And is there a color change? Now, if we look for those and we find at least 2 of them, it is a very, very good indication that we have a chemical change. So we're going to go ahead and flip this over. And we can see mixing a solid and a liquid gives us a gas. Gives us a gas. Now, if you know what that gas is, go ahead and comment down below. We'll talk about that later on, because we're going to see another example of that gas forming. So comparing the two, we saw lots and lots of bubbles form for this one. No bubbles, no gas, not exciting. Our chemical change, if we had a thermometer that could read the outside temperature of this, it would tell us that it did lose some heat. It did lose some heat, it cooled down. Our color still looks pretty much the same, but because we found 2 of those, we found the new state of matter, or the gas forming, and then we found the temperature change. That gives us a good idea that it is a chemical change. That's right. So we'll move those over here. And we're going to take an Alka-Seltzer here. Whoopsie. We're going to take an Alka-Seltzer here, and we're just going to drop it in this beaker of H2O. So again, dropping that Alka-Seltzer in there, we can see there is a chemical change. So what's happening here is very similar to what we had with our vinegar and baking soda. So we have citric acid, which is going to be our acid for the reaction, and then we have sodium bicarbonate, which is actually baking soda, which is going to be our base for the reaction. And when those two combine, they create lots and lots of cool bubbles for us. So these 2 experiments are almost identical. All right, so we do have 2 more experiments for us to take a look at. And this one, we definitely want to see a temperature change. So our thermometer is reading right around 80 degrees. It's a little warm in here right now. For this, we're going to take 3 ingredients and mix them together rather than just 2 this time. So for the first one, we have H2O2. So if you remember, I said H2O was our water. Comment down below if you know what our H2O2 is. So we'll pour this in. And I'll make sure to let you know before I add our final ingredient, the answer to that one. Next, what we're going to do, we're going to take about 40 milliliters of water, and we're mixing in some Ki, which is potassium iodide. Now that might be a little bit hard to see. I'll bring it a little closer. And we'll just stir that up. Now again, we can see a slight color change. You can see it did turn that yellowish color. But there is no temperature change, and we didn't have the creation of a new state of matter. We didn't have the transformation of another state of matter. So that tells us that it was a physical change. Very good. So with a physical change, we can get those ingredients back simply by boiling our solution here. Our water will boil away, and then we'll get rid of our water and keep our potassium iodide crystals. So in here I placed that H2O2, and if any of you got it correct, it was hydrogen peroxide. Oh man, Hydrogen Harry, I miss him. If you're watching out there, virtual hugs. What we're going to do now what we're going to do now, we're going to mix these two together. So I have my solution of potassium iodide, and I have my hydrogen peroxide in here. Now this is an experiment that you can try at home, but not in this manner. So what we're using is actually 30% hydrogen peroxide, which is 10 times as concentrated as what you would find at home. And if you've ever seen a bottle of hydrogen peroxide, you've probably never come in contact with a clear version of a bottle of hydrogen peroxide. And the reason for that is hydrogen peroxide is constantly breaking down to water and oxygen. So light, when it actually hits the hydrogen peroxide, is knocking off those extra oxygen molecules. If we were to leave this out long enough, we would see bubbles start to form on the side of the container. So that is an experiment you can try at home. Pour some hydrogen peroxide into a clear container and check out how the bubbles form on the outside. That's due to the light knocking off those extra oxygen molecules, going from H2O2 into just plain old H2O plus oxygen. So we're going to speed that process up. And to do that, we're going to use the Ki, or the potassium iodide. Now what this is called, this is a catalyst. So catalysts, they see a chemical reaction going along nice and smoothly, and they come in and they speed things up. It's kind of like giving somebody coffee or giving me coffee, and it gets them really excited, and these things happen really, really quickly. So we're going to make that happen right now. Going to get an extra container just in case it gets a little messy. The missus said I have to make sure to keep everything on the counter. I'm going to grab a little soap just to make it a little messier, but it'll be clean, right? So what we're about to make, you've probably seen before, and you've probably heard it called Elephant Toothpaste. And that's exactly what we're going to make. So we've got our ingredients in there. Now I'm going to add just a couple more. So I've got some food coloring here, and what we're going to do, we're going to run it along the side of the container. So again, as I mentioned, this is definitely something that you can try at home. We do have a safer method, and we'll actually be posting that online next week. So make sure to check out our Facebook page. Stay tuned to all of our social media channels for updates on that and all of our virtual science programs. So you can see I've got some nice food coloring going along the side there. And we're going to add our final ingredient. I'm also going to add the thermometer so we can see what the temperature change is. Give me a countdown from 3, 2, 1. All right, so we can already see some bubbles starting to form. And there they go, very, very quickly. I'm going to place this just over this container, because again, the life said I have to keep the place nice and clean. So we can see our elephant toothpaste forming. And in a moment, this is going to get too hot for me to hold, so I'm going to have to place it down. But I'll bring this over to you so you can see that steam forming from it. All right, and I am glad I put that in that container. Otherwise, I would have a big mess to clean up. So if you can see that steam forming off of the hydrogen peroxide, that is the water boiling in there because it's gotten so hot, as well as the oxygen molecules coming off the top there. So you can see I added red or purplish food coloring, and I also added blue food coloring. So we're going to check our temperature in here, and it is reading about 60 degrees Celsius or 140 degrees Fahrenheit. That is so hot. Does anybody know what temperature water boils at? Go ahead and drop that in the comments below, Celsius or Fahrenheit. Or, if you know this one, you can put it in Kelvin. So what just happened? What just happened? So remember those oxygen molecules? They were leaving the hydrogen peroxide already. We just sped that up with our catalyst. It made it happen really quickly, and all the bubbles stayed in there because we trapped them with our soap. Awesome. So we're going to leave this over here on the side. So as that changed into a gas, so as it went from a liquid into a gas, we saw that the steam was going up. And if you remember when we did our liquid nitrogen show on the first week, we also had our gas forming from a liquid. So with our gas forming from a liquid, it gets much lighter. It takes up a lot more space than it would as a gas. Also, our elephant toothpaste, we saw a couple of things happen. Actually, we saw all three. Had I not put the food coloring, we would have seen the color change happen a lot better, but there's definitely a color change that occurs. We saw the temperature change, and we definitely saw those bubbles form. So we know that this was a chemical change. Awesome. All right. So we have one final experiment, and then we're going to take some questions. So make sure that you comment down below if you have any questions that you would like to ask. So what we're going to do here, I have a solid. It's called calcium carbide. And that red label on it there tells you it is a little bit dangerous, but that's okay. I am practicing with all of our safety precautions. So I'm going to get this plastic out of here and grab a lighter. And if I try to ignite this right now, we can see nothing happens. Nothing happens to it. So it looks just like a rock. Well, all that changes when we add a little bit of H2O. So you can hear those bubbles forming already, and those bubbles will burst into flames. So our calcium carbide actually creates acetylene gas, which is extremely flammable. So once again, we'll take a look at that. And we can see that gas that that rock that we could not get to ignite actually does ignite now. All right. So I'm just going to move this outside. That way it ventilates a little bit. All right. Don't want that stinky stuff in my house here. All right. So I'm going to go ahead and check out the comments here. So once again, with that calcium carbide, as I added the water, there was definitely a physical or a chemical change. You're right. It was a chemical change. So we had those bubbles that started to form, and then those bubbles were actually able to be ignited. And it gave us a really cool little explosion in there. All right, so we're going to check out our comments down here and see if I can't answer some questions that you may have. Whoa, that's me. All right, wow, fire. Yes, I love the enthusiasm. All right. Once again, if you have any questions, please ask them down below in the comments. Or I guess if you're looking at it on the iPad, over to the side in the comments. Peroxide. Hydrogen peroxide is H2O2. Awesome. Josie, Selena, Stephanie, Jennifer. You guys got that perfect. What made the fire? Very good question. What made the fire? So as we added that water into the container, it reacted with the calcium carbide and it created acetylene gas. Now this is a gas that people use as fuels for torches and for welding. So it is a gas that burns fairly hot, but with our experiment here, it burned very quickly because those bubbles take a little too long to form, so they don't continue to stay ignited. That is a very good question. Thank you for that, Aaron. This one comes from Selena. What is a sign of a physical change? What is a sign of a physical change? So again, if we can get our original ingredients back from our experiment. So with our physical change in our salt water, we didn't have those signs that tell us it was a chemical change. So if those signs are absent, it tells us we probably have a physical change. Awesome question, thank you. Keep them coming, I am ready. All right, I am searching. Please comment down below if you have any more questions. I'd like to say hi to Bradley and Blair from camp. I see that you guys are missing us. We miss you too. Can we use lower concentrate hydrogen peroxide for the experiment? That is an awesome question. So again, you'll want to look out on our Facebook page for a video that we're going to post next week wherein you can do the elephant toothpaste yourself at home. So you're going to be using different ingredients. Now, not everybody can get their hands on this 30% concentrate. So what you will be using is the 3% concentrate. So the potassium iodide is also a bit of a pricey investment. So what you can use is some store-bought yeast. So again, be on the lookout for exactly the ingredient list that you need and a video demonstrating exactly how you can achieve those same results that we did with the elephant toothpaste in your own home. It is super simple, and again, it is super fun. Why did the elephant toothpaste get hot? Why did the elephant toothpaste get hot? That's an awesome question. So it is what we call an exothermic reaction, which means that it gives off heat. So it requires the heat to be able to give off those gas molecules of the oxygen. If you remember our vinegar and baking soda, I said it got colder. It dropped in temperature. Now something that drops in temperature, we call an endothermic reaction. So endothermic, it gets colder. Exothermic, it gets warmer. What happened to the elephant toothpaste after it exploded? This comes from Matthew, age 10. I just put it in my sink for a little bit of an easier cleanup. So again, those bubbles that were formed, those are oxygen bubbles, and it leaves us with soap and water. All right, so I've got a couple more questions here. Can you use the toothpaste on an elephant? Now that is an extremely silly question because I know elephants don't brush their teeth. But even if they did, this is probably not something safe that you would want to use on your pet elephant. Stephanie asks, will the balloon float if you take it off? That is an excellent question. So inside of our balloon, we had carbon dioxide that formed. I did not answer that for you. I told you I was going to. So we had carbon dioxide that formed, and let's see if I can tie this with gloves on. And carbon dioxide is actually heavier than normal air. So carbon dioxide is a heavier substance, although it's a gas and it's colorless, odorless, it is still heavier than regular air around us. So to get our balloon to float, we would need something lighter than air, like hydrogen. Hydrogen, Harry? Or helium. Helium would work too. All right, we have 2 more questions here. 2 more questions here. Why is it called Elephant's Toothpaste? Well, that's an excellent question. The reason they call it that is as it comes and foams out of the container, if you pour those colors perfectly, I did not, I'm sorry. But if I did pour them perfectly, it would have looked like a giant tube of toothpaste being squeezed out. Maybe one large enough to fit an elephant's mouth. All right, and our final question here, does the gas from the elephant toothpaste smell? Well, the gas from the elephant toothpaste is just oxygen, but it does mix in a little bit with the smell of the soap. So I smelled some Super Dish Soap Deluxe with plant-based formulas and essential oils. It smelled absolutely fabulous to me, but the gas that comes off of it is completely odorless. I want to thank you guys so much for joining me today. I know this was a little bit of a different style, a little bit of a different experiment, just me alone. I hope you enjoyed it, and we look forward to seeing you next week. Don't forget to look out for Hydrogen Harry himself. He will be on here live next week. Again, please stay safe, stay healthy, stay happy, and virtual hugs to you all. Thank you.